All right, I believe we're recording now. So let's go over this practice exam, or this old exam from, I believe, the year 2000, could be 2021. The first part of the exam is over proton NMR spectroscopy, in which I gave them 8 structures and 6 spectra, and they had to match the spectrum to the structure. I would expect a similar section to be on your exam. So, the first spectrum looks like this. And the first thing I notice when I look at this spectrum is that we have a 6H triplet, a 4H multiplet, and a 4H triplet. The 4H resonances cannot be CH4. And the 6H resonance certainly cannot be CH6. So there has to be some kind of plane of symmetry. And I believe what we're looking at here is 2 methyl groups. Two CH2s over here, and another 2 CH2s over here. And furthermore, the CH3s have to have a CH2 next door because they are split into a triplet. 2 protons in the CH2, 2 plus 1 equals 3. Remember, you get splitting from the protons that are next door. And there seems to be a CH2 next to this other CH2 over here. So what that says to me is that the CH3, CH2, CH2 are all connected to one another. And then the methyl group is split into a triplet by the adjacent CH2, and the CH2 on the end is also split into a triplet by the adjacent CH2. The CH2 that's on the end is going to be connected to something fairly electronegative for its chemical shift to be pulled down to 2.5, like this. So we have 2 propyl groups in the molecule, each connected to something in the middle. And when we look at the structures that were given, the only one that fulfills that is compound X. In which we have 2 propyl groups attached to NH. And the NH resonance does show up on the proton spectroscopy. Remember, you can see hydrogens. You can't see other elements, but you can see hydrogens. So that's this broad 1H resonance over here. That's for the NH. Other than that, everything seems to add up. And all the chemical shifts make sense. So I think we can be confident saying this is compound X. In the second spectrum, we have a 3H triplet and a 2H doublet. And I believe we talked about that in class. That's a clear signal for an ethyl group. The 3H, the methyl group, is split into a triplet by the adjacent CH2. and the CH2 resonance is split into a quartet by the adjacent CH3. In both cases, you add 1 to the number of next door H's. The 3H resonance has 2 H's next door, 2 plus 1 equals 3. That's where the triplet comes from. The 2H resonance has 3 protons next door. 3 plus 1 is 4. That's where the quartet resonance comes from. So this is going to be the CH3 of the ethyl group. And that's going to be the CH2 of the ethyl group. We also have a 3H resonance and a 2H resonance down in the aromatic range. But let's not be so fast to call that a CH3 and a CH2. Because again, 7.5 parts per million, you're looking at hydrogens that are in the aromatic range. And we have a total of 5 of them. So that speaks to me of a monosubstituted aromatic ring. If one of the hydrogens on benzene is replaced with something else, then that leaves 5 hydrogens left over. And they often find themselves in a 3-to-2 ratio. The 3 hydrogens of type A are here slightly upfield of the 2 hydrogens of type B. Now you'll note that of the A protons, you've got 2 protons that are ortho to the other group and 1 proton that is para to the other group. The orthos and the para are technically distinct from one another. However, they're so similar in chemical shift that they just fall on top of each other. And that's something that will happen sometimes. So what you need to know is that in a proton NMR spectrum, sometimes peaks will fall on top of each other that are technically of different types of hydrogens, but that are so similar that they can't be distinguished. We didn't run into that problem with carbon NMR spectroscopy. It's something unique to proton NMR spectroscopy. But it's not so surprising that the orthos and the para should be so similar, because in chapter 16, we learned about ortho-para directing groups. That suggests that the ortho and para positions have some similarity to each other chemically. So the fact that the ortho and para protons should fall on top of each other is not so outlandish. And then the 2 metaprotons show up on their own. So all we have to do left is to connect these pieces. We've got an ethyl group and we've got a monosubstituted benzene ring. That leaves 2 possibilities, compound S and compound T. So how do you know which it is? Well, the way you know which it is by the chemical shift of the CH2 group that's in the ethyl group. We need to ascertain whether that CH2 group is attached to an oxygen or not. Because in compound S, the CH2 is attached to an oxygen. In compound T, CH2 is connected to the benzene ring. And so the way we know is by the chemical shift. If you look at where the CH2 group shows up, it's at about 2.5. That's the right chemical shift for the CH2 to be attached directly to the benzene ring. If the CH2 were instead attached to O, like in compound S, then we would see the CH2 group at more like 4 parts per million. So it's not a subtle difference. It's a pretty dramatic difference. It's not like 2.5 versus 2.6. It's more like 2.6 versus 4. So since the CH2 is at about 2.5, 2.6, we know that the CH2 is attached directly to the benzene ring. In other words, we have ethylbenzene or compound T. As it turns out, compound S is on this exam. And I think you can already see the difference. There's your methyl group. There's your methylene, your CH2. That's right, that's not going to work. Let me try one more thing. No, it doesn't look like we're going to get anywhere. So once again, our ortho and para protons are going to fall on top of each other. And our two metaprotons will have a different chemical shift. So here's the A protons in a 3H resonance. And here's the B protons in a 2H resonance. So the most significant difference between the two spectra, I mean, I guess the aromatics show up in slightly different chemical shifts. Interesting, the A protons have moved upfield. But the CH2 resonance of the ethyl group is at 4.1 parts per million. That's just about the right range for the CH2 to be attached to oxygen. Remember, you cannot see the O on a proton NMR spectrum. You can only see H's in a proton NMR spectrum. But 3.5 to 4 parts per million or thereabouts is just the right range for protons that are alpha to an oxygen. And so instead of CH2CH3 being attached here, we have OCH2CH3. In other words, compound S. So the main giveaway is the chemical shift of the CH2 group. Moving back to spectrum C. Looks to me like we have a 3H singlet. That can pretty much only be a CH3 that's attached to something with no protons attached. So I'll put CH3X. No protons next door, 0 protons next door, 0 plus 1 equals 1. You get just one peak. Besides that, we have a 6H doublet and a 1H multiplet. And pretty much the only thing that could be, as we discussed in class, is an isopropyl group. we'll call the methyl protons of type A. The A protons are over here. And they're split into a doublet by the one adjacent B proton, which is down here. So our pieces are a methyl group, an isopropyl group, and something that we can't see that moves the methyl group down to 2 parts per million and also means there's no adjacent protons to the methyl group. So looking at my choices that have an isopropyl group attached, the only choices are U and Z. And of the two, I think Z matches better because Z is a CH3 attached to C double bond O. And then on the other side of the C double bond O, we have our isopropyl group. And the chemical shift of both the methyl group and the B hydrogen are at about 2 parts per million, 2 something in any case. That's typical for hydrogens that are next to a carbonyl. The A hydrogens are split into a doublet by the adjacent single proton that we've labeled B. So I think the best explanation is that we're looking at compound Z. That's the one that's the most consistent with this spectral data. In the next spectrum, we again have an isopropyl group because I see a 6H doublet. We'll call the A protons the ones on the methyl groups. And the B proton, the lone hydrogen on the isopropyl group. We can also see a CH2 group. Rounded about 2.4 parts per million. And way down at almost 10 parts per million, we see a CH. There's just one hydrogen here. So you need to know that between 9 and 10 parts per million, is where aldehyde hydrogens show up. So there's an aldehyde. So our pieces are isopropyl group, CH2, and aldehyde. And there's only one way to put all those together. The CH2 has to go in the middle. There's our isopropyl group. Here's our CH2. And finally, here's our aldehyde group. The A protons are over here in the methyl groups. The unique B proton is up here. And then our CH2 is over here. So in other words, we're looking at compound U. Last but not least, we've got compound F, or rather spectrum F. And in spectrum F, I see a 2H doublet. That tells me I'm looking at a CH2. And then right down here, not quite in the aromatic range, these protons are vinylic protons. Vinylic means they're involved in C double bond C. So there's two vinylic hydrogens that are different. That looks to me like we have a situation like this, in which the two vinylic hydrogens are on adjacent vinylic carbons. There have to be two carbons involved in the vinylic group, because in order to have a C double bond C, you need two carbons. So something like that looks to be the case. So if we suppose, as is reasonable, that the CH2 is attached to one of those vinylic carbons, then we have a situation like this. And since we've accounted for all of the hydrogens, all four hydrogens, that means the molecule must be symmetrical. And there has to be a plane of symmetry running down the middle of the molecule. Like this. So instead of 2H, it's actually 4H. Instead of each of these being 1H, it's actually 2H for each of them. There's this hydrogen and this one up here. That's the same. And there's this hydrogen and this one up here that are again the same. So this can only be compound W. The way we know it's not compound Y is because Y also has a plane of symmetry. But the ratios are wrong. Instead of the ratio being 2 to 1 to 1, the ratio would be 1 to 1 to 1. Cyclopentadiene is also a symmetrical compound. But instead of the ratio being CH2 to CH to CH, it's CH to CH to CH. So the ratio is wrong. The integrals are wrong. So it cannot be compound Y. It must be compound W. And that's pretty much it for the spectra. The next question is a combination spectroscopy problem, in which you're given a proton NMR, a carbon NMR, an IR, and a mass spectrum. Now you have some pretty good practice problems. I put up a bunch of practice proton NMR problems that are kind of similar to this, in which they give you the proton NMR spectrum plus the molecular formula. Here you're given the proton spectrum, the carbon NMR, an IR spectrum, and a mass spectrum. And the idea is to get from the mass spectrum the molecular formula, and then proceed from there. I also want to point out to you that I've updated your proton NMR class notes at the end of the class notes with a step-by-step method for solving combination spectroscopy problems. I'm about to demonstrate that method and how it works. But basically, you start with the mass spectrum. So I can't keep all these things open on my screen at the same time, but you might want to have that method open. You might want to have your class notes open while viewing this part of the review session. So notice in the instructions, it says the compound contains only carbon, hydrogen, and oxygen. So step one of what to do in this type of question is to look at the mass spectrum. And we can see the molecular ion very clearly at 126. It even says the molecular ion peak is at 126. So that means that our compound has a molecular weight of 126 AMU. And what I think makes the most sense to do in terms of how to proceed from the beginning is to assume that you have exactly one oxygen. Now, oxygen weighs 16 AMUs. So if we subtract out the oxygen, that leaves 110 AMUs for the carbons and the hydrogens. In other words, we're going to assume that the molecular formula of our compound is CXHYO with exactly one oxygen. We've accounted for the oxygen already in the 16 AMUs that we subtracted from 126. This is exactly the method I suggest you follow on the exam. Assume there's exactly one oxygen. If it doesn't work out and you can't find a reasonable molecular formula, then try 2 oxygens. But start with just one. Start by assuming there's just one oxygen. And so the remaining 110 AMUs are for the carbons and the hydrogens. So how many carbons are there? Well, we know there can't be 10 carbons because carbon weighs 12. 10 times 12 is 120. That's more than 110. So there cannot be 10 carbons. There cannot be 9 carbons either. Because if there were 9 carbons, 9 times 12 is 108. 110 minus 108 is 2, and you have only 2 left for hydrogens. C9H2O. That doesn't make sense. So we throw that out. You can't have just 2 hydrogens with 9 carbons. So let's try 8 carbons. 8 times 12 is 96. (110 minus 96). Leaves 14 AMUs for the hydrogens. In other words, we're looking at a formula of C8H14O, and that's a very sensible molecular formula. It has 2 degrees of unsaturation. If it were fully saturated, it would be C8H18O, but it's C8H14O. That means the index of hydrogen deficiency is 2. There's 2 rings or pi bonds. Good. So we have a working theory for our molecular formula. We'll go with it. That's step 1, is look at the mass spectrum and try to figure out the molecular formula. Step 2 is you look at the IR spectrum and see what you can find from there in terms of functional groups that are there, and equally importantly, functional groups that are not there, that we don't see in the IR spectrum. And I don't see an alcohol. I don't see a carboxylic acid. We couldn't have a carboxylic acid anyway with only 1 oxygen. What we do see is this very prominent peak at about 1,720 parts per million. That indicates a carbonyl. That's a carbonyl stretch. So write that down. Everything you learn, write it down. I can also tell that all of my CH stretches are below 3,000 wave numbers. That means we don't have any C double bond C. There's no alkene. There's no aromatic ring. And it wouldn't make sense for there to be either of those things anyway, based on the molecular formula that we have hypothesized. So we have a carbonyl group and not a whole lot else in this molecule. That's step 2. Learn what you can from the IR. Step 3, look at your carbon NMR spectrum and see what you can learn from there. And in the carbon spectrum, we see 6 peaks, but there's 8 carbons. So that means there has to be some kind of plane of symmetry. There has to be some symmetry to the molecule in order for there to be 8 carbons, but only 6 peaks. Notice that we can very clearly see the C double bond O right over there. I'm not sure what just happened. Anyway, that's the carbonyl peak. So there's only 6 types of carbons. That means there's a plane of symmetry in the molecule. I see, it's covering it up somehow. So we've learned something more about the structure. And last of all, look at the proton NMR spectrum. See if you can account for all of the hydrogens. Looks to me like we have a CH3 over here. In fact, the CH3 that's next to a CH2, because the CH3 is split into a triplet, and then the CH2 is down here. There's the 2H resonance. Then finally over here, we have a CH. So we have a CH and CH3CH2. Next, we have 2 4H multiplets, which again, we've learned they're not going to be CH4. This looks to me like 2 CH2s. Or both of them. And those are the only hydrogen resonances. So having twice 2 CH2s also speaks to the symmetry of the molecule. Let's see if we can account for all the hydrogens. There are 14 hydrogens. 3 plus 2 is 5, plus 1 is 6, plus 4 is 10, plus 4 is 14. So we've accounted for all of the hydrogens. With, again, the plane of symmetry. It almost looks to me like we have our carbonyl. We have two doubled sets of CH2s. And then down here we have CH, then CH2, CH3. And a plane of symmetry running down all of it. Something like that. So we have our two sets of two CH2s. This is one, and this is one. And from that, it looks to me like we've almost drawn a molecule. All we need to do is connect everything into a six-membered ring. So C double bond O, two CH2s, two more CH2s, and then CH, CH2, CH3. Let's make sure the formula is C8H14O, 1, 2, 3, 4, 5, 6, 7, 8 carbons. As for the hydrogens, 3 plus 2 is 5, plus 1 is 6, 8, 10, 12, 14. So it fits our molecular formula. If you wanted to at this point, you could go back to your mass spectrum and see if, for instance, you can see the ethyl fragment. I'm quite confident you will at 29 AMUs. But at this point, I think we can be reasonably confident that this is the structure of our compound, which indeed it is. Now, I will say, I thought this one was pretty tough. I went pretty tough on this group of students because their exams were open book. This was the COVID semester. So I will say to the students in spring of 2023, you will have a problem like this on your exam. I believe it's easier than this. But this one was pretty tough. The next page is on carbohydrates. So it says D-talose is an aldohexose like D-glucose, except it differs in configuration from glucose at carbons 2 and 4. And it says draw D-talose in its open chain form, its chair form, and its Hayworth projection. The way we did on YouTube, meaning the way we did in class. And then for the two cyclic forms, draw the beta anomer. So just so we don't forget, let's get our glucose out. And recall that CHO means an aldehyde group. So that's D-glucose. As for the numbering of the carbons, 1, 2, 3, 4, 5, 6. And it says D-talose is just like D-glucose, except at carbons 2 and 4. So we need to flip the configuration at carbon 2 and carbon 4. So instead of the right, left, right, right of glucose, we will have left, 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 right. And this is the open chain form of D-talose. As for the chair form, here's glucose in the chair form. You'll note that all of the OHs are equatorial. I did it in the beta anomer because the problem says to draw the beta anomer. One, 2, 3, 4, 5, and 6. And then over here, we've got the beta anomer. So that's how glucose looks. We need to switch the configuration of carbons 2 and 4. So we need to make the 2 and 4 OHs axial rather than equatorial. And that's exactly what we've done over here. And then from this, we get the Haworth projection. I do not recommend memorizing the Haworth projection of glucose. I don't think it's a good use of your time. I've never memorized it. Whenever I need to draw a Haworth projection, I just get it from the chair. And interestingly, all of the groups point up for beta D-talose. This OH points up on carbon 1. This OH points up. This OH points up. This OH points up. And the CH2OH group points up. The CH2OH should always point up if you're looking at a D sugar. So there's your Haworth projection. Next part of the question says to draw L-talose and L-glucose in their open chain forms. So remember, when you go from a D sugar to an L sugar in the open chain form, you need to flip all of the OHs, not just the penultimate one, all of them. So if D-talose is left, 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 right, then L-talose is right, 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 left, and should look like this. If D-glucose is right, left, right, right, then L-glucose should be left, right, left, left, just as we have over there. There's L-glucose. Remember, CHO means an aldehyde group. Then it says draw the only 3-carbon sugar we discussed in class that is not chiral, and that would be 1,3-dihydroxyacetone. That's a metabolic intermediate. We'll meet that in chapter 29 if we haven't done that yet. Good. And then to draw the disaccharide D-glucose beta-1,6-D-glucose. So we start by drawing our first glucose. All of these 3 OHs and the CH2OH are equatorial. and it says we want a beta 1,6 linkage. So we're going to start at carbon 1 of the first glucose. You always start at carbon 1 of the first glucose. At least in general, that's going to be the case. And you make it beta, meaning the oxygen is going to point up or equatorial. And then we simply connect that oxygen to carbon 6 of the next glucose. Carbon 6 is the CH2. So that's attached to the ring down here. This is our second glucose molecule over here. Then it says, at the hemiacetal carbon, draw the alpha anomer. So the alpha anomer has the OH pointing down on the hemiacetal carbon. So that's what that disaccharide looks like. We have a beta 1,6 linkage over here. Let me label that for you. This is carbon 1, 2, 3, 4, 5, 6, we have a beta linkage over here. That connects to carbon 6 back here. 1, 2, 3, 4, 5, 6. And then at the hemiacetal carbon, draw the alpha anomer. So there's a fully numbered and labeled diagram. On the next page, we have some synthesis questions. I called them OWL-style syntheses because we were using OWL at that point rather than active. But active is similar questions to this. So in a question like this, you just need to fill in the reagents. And it requires knowing what each type of reaction is. So here we're going from C single bond OH to C double bond O. And you need to know that's an oxidation reaction. We're oxidizing a secondary alcohol to a ketone. And you can find out about that reaction in 17. I think 17.7, but I know it's in chapter 17. And so you need an oxidizing agent. The preferred one we learned about in chapter 17 was Dess-Martin periodinane, DMP. You could also use PCC, pyridinium chlorochromate. You could even use chromium 6 oxide. Any similar chromium reagent would be fine. Then, in the next step, we've had an isopropyl group come in and attack the C double bond O. So we go from C double bond O to C single bond OH again, from the nucleophilic attack of the isopropyl group onto the carbonyl carbon. So the traditional way this type of reaction is done is by a Grignard reaction. So the reagents are isopropyl magnesium bromide or magnesium chloride or magnesium iodide. It doesn't have to be a bromine. In diethyl ether solvent, followed by H3O plus workup, because at first you get O minus and you need to put the H back on the oxygen. So you need to protonate the oxygen. So you need an acidic workup. That gives us this tertiary alcohol. Then in the next step, we go from the tertiary alcohol to an alkene. In other words, we've lost the OH and we've also lost an H. We've lost water to form a double bond, also called a dehydration reaction. And in order to get that done, you need a good dehydrating agent. Sulfuric acid would work. Phosphorus oxychloride might come to mind. I think I accepted any reasonable dehydrating agent. Thionyl chloride is fine. Even acetic anhydride is fine. In the next step, we go from the alkene to an OH and a Cl attached to those two carbons. In other words, we formed a halohydrin. And you can find out about that reaction in chapter 8. The reagents necessary are chlorine and water. And we went over that reaction in chapter 8 along with its mechanism. And then, last but not least, we go from the chlorohydrin to an epoxide. And that's a chapter 18 reaction. That's essentially a Williamson ether synthesis, which is also an SN2 reaction. A Williamson ether synthesis is nothing more than an SN2 reaction. So to carry it out, you need a base to pull off the proton from the OH to get O minus. And then O minus attacks the carbon that bears the chlorine and expels Cl minus as a leaving group. And you get the epoxide. In the next synthesis, we start with an alkyne and go to a cis alkene. So this is a reduction reaction. We reduce the alkyne to a cis alkene. And the reagent of choice for that is hydrogen and Lindlar's catalyst. You can find out about that reaction in chapter 9. Then remember, CO2H means C double bond O OH. It means a carboxylic acid functional group. So in this step, we go from carboxylic acid to acid chloride. And that requires thionyl chloride. We learned about that reaction in chapter 21. That's conversion of a carboxylic acid to an acid chloride. And again, thionyl chloride is the reagent of choice. Next, we convert the acid chloride to an ester. And that's done by alcoholizing the acid chloride. And you can find out about that reaction in, I believe, 21-4. And then, last but not least, we have a Diels-Alder reaction. We're going to use this ester as our dienophile, and our diene is cyclopentadiene, and you get this compound here. Or let me show you another way to draw that compound. Whoops. So that's another way to draw it. Either way is perfectly acceptable. And in the last reaction sequence, we start with a carboxylic acid. Remember what CO2H stands for. We set up here what CO2H stands for. It's a carboxylic acid. And in the first step, we're installing a bromine next to or alpha to the carboxylic acid. We learned about that reaction in chapter 22. And there we learned the reagent of choice is bromine and phosphorus tribromide in the first step, followed by an aqueous workup. And that installs the bromine next door to the carboxylic acid. And then all we need to do is 2 successive SN2 reactions with a nitrogen. In other words, we need to treat this compound with an excess of ammonia. This is just an SN2 reaction. You can find out about those in chapter 11. So the reaction starts by ammonia acting as a nucleophile and kicking out bromide as a leaving group. And that gets the nitrogen attached to the chain. Then we lose a proton, either another ammonia molecule comes in and takes the proton off or something like that. And the NH2 attacks right here to expel bromide again as a leaving group, and you close the 5-membered ring. And this, by the way, is proline. That's an amino acid. So much for the synthesis questions. Next page is drawing the products from the starting material and the reagents. The first question starts with a sugar, and it undergoes reduction with sodium borohydride. So this is a reduction of an aldose to a sugar alcohol using sodium borohydride. That's in chapter 25. Sodium borohydride is the reagent of choice. And indeed, sodium borohydride will reduce any aldehyde to a primary alcohol. Let me just remind you again what CHO means. So the aldehyde gets reduced to a primary alcohol. And you get a sugar alcohol, also known as an alditol. Next reaction is a Michael reaction. And let's use this as an opportunity to review the Michael reaction. The reason I know it's a Michael reaction is because I'm given a species that can make an enolate by deprotonation. And I'm also given an alpha beta unsaturated carbonyl compound. That's going to act as my acceptor. The nucleophile is going to be an enolate as per usual. So my base is ethoxide. And as I always like to say, you'll notice that I'm not even showing the sodium. Do not show alkali metal ions in mechanisms, ever. Do not show alkali metal ions in mechanisms, ever. It's always wrong to show them. They play no role in the arrow pushing. They're just spectator ions. There are no exceptions. It's always wrong to show them. So the first step is formation of the enolate. So there's your enolate. The enolate then adds into the alpha beta unsaturated species. Like so. So that's the new bond we just formed. So you get the enolate, and then the enolate gets protonated using a molecule of ethanol. Like so. So you get this trione. Now, if we were drawing the full mechanism out, we would then need to show ETO minus deprotonating this proton right here, since it's quite acidic. It's between two carbonyls and also next door to, no, I guess it's not benzylic, but it's still pretty acidic being next to two carbonyls. So you'd show that getting deprotonated, then you'd add H3O plus and put the proton back on. In either case, the structure of the final product is like this. And I think you'll see that's what we have over here. I also accepted this one, since this could come about by an intramolecular aldol addition, deprotonating here on the methyl group, then the enolate attacking this carbonyl, followed by protonation and dehydration. I don't think you'd even need to heat this one because the double bond that you get is conjugated to both carbonyls. So there's a very strong driving force to losing water. So I don't even think you'd need to heat it. But we accepted both answers. The next one is an aldol condensation. And the way I know that is because I'm treating the enolate that I get from this species with an aldehyde or ketone. Again, remember, PHCHO is benzaldehyde, PH, C double bond O, H. So the enolate attacks the benzaldehyde carbonyl carbon. We protonate the O minus. We lose water once again. And this is another one I don't think you'd need to heat because the double bond is conjugated to the benzene ring as well as to both carbonyls. So I don't even think you'd need to heat it. So that's a classic aldol condensation reaction. The next one is again formation of the enolate. Again, you'll notice we treat it with a base. That's going to pull off a proton here. And then we simply alkylate the enolate with 1-bromobutane. So the enolate attacks the 1 carbon of 1-bromobutane, kicks out bromide as a leaving group, and we attach a butyl group to that carbon. So this is just alkylation of an enolate. That's a chapter 22 reaction. The next one is another aldol condensation reaction. And the way I know that is because it says 2 of this molecule, and that molecule is a ketone. So 2 ketone-aldehyde molecules come together in an aldol condensation reaction. And here I even put heat just to drive the point home that we're going to dehydrate. I just didn't want there to be any doubt. So I mentioned heat. There's your new double bond that you get right there, conjugated to the carbonyl. So that's the aldol condensation product of that particular ketone. And the last one is involving 2 ester molecules. So I expect you to recognize an ester functional group at this point. This is a Claisen condensation. And the new carbon-carbon bond that we form is right here. So you just go through the very same mechanism of the Claisen condensation that we did in class. You had lots of practice on that on the active also. Next, we come to our mechanisms. The first mechanism is of a Claisen condensation once again, because you're reacting an ester enolate with an ester. So it says reacting this plus this. So in the first step, my base, my ethoxide ion, deprotonates alpha to the carbonyl of the ester. This is the only species from which we can make an enolate. The other one is fully substituted at the alpha carbon, so we can't form an enolate of this one. There's no protons on that carbon. So we form the enolate. The enolate then adds into the other species, and we get this intermediate. Then, just like in every Claisen condensation, the intermediate collapses. The O- donates in an electron pair to make C double bond O and expels alkoxide as a leaving group. That gives this intermediate. It makes an ethyl ester functional group. Well, we already had the ethyl ester functional group. I'm not sure why I turned the molecule upside down, but I did. Then, since we're still in alkaline solution, we have to show this acidic proton getting pulled off by the base that we have present in solution. Our base is still sodium ethoxide, and we're still under alkaline conditions. So the base pulls off this proton and we make the enolate. And that's what's going to be in solution until we add the H3O+. The first thing the H3O+ will do is neutralize the sodium ethoxide, and then it will get to work on this enolate and start protonating it. So electron pair comes in to reform C double bond O. We break the carbon-carbon pi bond. those electrons shift out to pull off a proton from H3O plus, and we get the product. So that's a typical Claisen condensation reaction mechanism, exactly like we did in class. And I should mention that's in chapter 23. The next one is formation of a glycoside, which is in chapter 25. And the mechanism is also in 1910. We learned the mechanism at first in chapter 19. So this is just a rehash of that. The first step in formation of a glycoside is protonating the OH group that's on the hemiacetal. And for that, we use the conjugate acid of the solvent that we're given. So the conjugate acid of ethanol is shown right here. And we pull a proton off of that to give this intermediate. And then we lose water as a leaving group with help from one of the lone pairs on the oxygen. And that gives this intermediate. And now, since in this case, it is showing stereochemistry, we want to show that we get the ethoxy group on the bottom of the molecule pointing down. So we show ethanol attacking from below. If it didn't show stereochemistry, then it wouldn't matter how we showed this step, as long as we showed ethanol attacking it. That breaks the carbon-oxygen pi bond and gives this intermediate. And now all we have to do is pull off this proton to get rid of the plus charge on oxygen, and we'll use an ethanol molecule for that. Ethanol is the only species around that's at all alkaline. And that gives us our product. So this is formation of a glycoside. All right, this next mechanism is an intramolecular aldol condensation. And the first thing we need to figure out is where the deprotonation is going to take place. You could deprotonate either here or here to get a six-membered ring. But the reason I knew to deprotonate over there is because this part of the molecule stays the same, with the carbonyl and the two methyls next door. So that indicates to me that this carbonyl needs to be the enolate, not the acceptor species. It's the other carbonyl that's the acceptor. So we look at the base we're given, it's OH minus. OH minus pulls off this proton and we get the enolate. And then we show the enolate attacking the other carbonyl at the other end of the molecule. I just realized I'm missing an arrow. That's better. And that gives this intermediate. And the new bond we just formed is right there between carbons 1 and 6. So the next step in the aldol condensation is protonation of the O minus. O minus picks up a proton from whatever the solvent is. I look at what I'm given. I see that we have water, so we'll use a water molecule in order to put the proton on. So that gives us the aldol addition product, as Active correctly calls it. Then, since we're given heat, and since we're also shown a product with the double bond, we know that dehydration has taken place. So remember, dehydration takes place in 2 steps. It happens by an E1CB mechanism, always. Whenever you're doing an aldol reaction in base, the dehydration is E1CB, always, no exceptions. The first step of an E1CB reaction is to deprotonate. So we deprotonate next to the carbonyl to make the enolate. That gives us this intermediate. So first step of E1CB, deprotonation. Second step of E1CB, loss of leaving group. So this oxygen with the minus charge donates inward an electron pair in order to reform C double bond O. The carbon-carbon double bond shifts over 1 spot, and we kick out OH minus as a leaving group, and we get the product. So that's, again, a standard aldol condensation. It just happens to be intramolecular. The mechanism is the very same thing as any other kind of aldol condensation. It just happens within the same molecule. That's the only difference. And last but not least, this is an iminium hydrolysis reaction, which we saw in chapter 23. And also in chapter 19, where we saw how imines and enamines are made. The mechanism of iminium hydrolysis is the same as the mechanism of formation of an imine or an enamine, except backwards. So it's the exact same mechanism, just step for step backwards. So in the first step, instead of losing water as a leaving group, water attacks. It attacks the C double bond N. Instead of C double bond O, it attacks C double bond N. Very similar thing. And we get that next intermediate. Let me just clear some space. So that gives us this intermediate. After nucleophilic attack, look for proton transfers. You probably are going to be on the right track. So first we need to remove a proton from this oxygen to get rid of the plus charge. And recall, when you're given H3O plus, that implies that H2O is also present. H2O is understood. So water pulls off this proton and gives us this intermediate. Now we need another proton transfer. This time we want to put a proton onto the nitrogen so that we can lose the nitrogen as a leaving group and break open the ring. And so we use H3O plus to put a proton onto this nitrogen. That gives us this intermediate. In the next step, nitrogen leaves as a leaving group with help from the OH oxygen that donates in an electron pair to make a carbonyl. And that breaks open the 6-membered ring and gives this intermediate. Now the only thing left is for water to pull off this proton to give us the product. And just as a reminder, and that's basically it for the practice exam, plus a little review of the Michael reaction. So hopefully that all recorded. It sure looks like it's recording. I will get this video up later today, hopefully. So enjoy the rest of your weekend. I'll see you all in class.